Have you ever wondered how we measure water in a container that is not flat and not perfectly shaped? In daily life, we calculate simple area. But what if a surface changes into direction at the same time? This question led us to double integral, a concept used both in engineering and science, as well as in digital visualization. I am new to ANDITA SEPTIA DEWI. My last ANDITA number is 006. Let's explore how mathematics help us measure space itself.
Okay, let's start with the purpose of this study. The first goal is to explain the concept of double integral in a conceptual way, not only through formula. The second purpose is to connect Riemann sum with their geometric meaning, so we can actually see what is happening behind the calculation. And finally, this study shows how GeoGebra can support learning, because visualization helps us understand idea more easily. Next, the Riemann sum approach. To understanding double integral, we begin with something familiar, which is the Riemann sum. Here, the regions omega is divided into small area. This is called delta A. Each small area from a tiny vertical rim, when it is multiplied by the function value. We have the function, this is the two integral omega, the function if x, y, di equal to lim sigma, the function is xi, yg, delta a. When we add all these tiny volume together, we get an approximation of the total volume. And as this area becomes smaller and smaller, the approximation becomes more accurate. So basically, a double integral represents the sum to infinitely small volume. Okay, now let's look at the formal definition. For a rectangular regions, omega equal to AB times CD. The double integral is defined as double integral of omega, the function of x, y, dA is equal to the integral a to b and the integral c to d, the function of x, y, dy, dA. This means we integrate one variable first and then the other. Based on Fubini theorem, the order of integration can be changed. For example, the integral a to b and integral c to d, the function of x, y, dy, dx equal to the integral of c to b and integral a to b, the function of x, y, dx, dy. So we can integrate with respect to x first or y first, and the result will remain the same. This makes calculation easier, especially when one order is simpler than the other. Okay? Next, the geometric meaning of double integral. This slide explains the geometric meaning of double integral. If the function of f, x, y written equal to 0 on the regions omega, then double integral omega, the function of x, y, dA. This is represent the volume of a three-dimensional solid. Are bounds by, first one is the surface z equal to function x, y, and the plane z equal to 0, and the projection of omega onto the xy plane. Or in the simple word, or in the other word, a simple integral gives an area under a curve, and double integral is give a volume under the surface. Now let's look at an example from the article. The function is f x, y equal to sin x plus 2 on the regions omega equal to 0,4 times 0,3. Then the double integral is double integral of omega, the function is sin x plus 2 dA equal to the integral of 0 to 3 and integral 0 to 4, the function is sin x plus 2 dx dy. The first step, we integrate the function with respect to x. Then the integral 0 to 4 sin x plus 2 dx equal to min cos x plus 2x. Evaluate from 0 to 4, then equal to 9.653. The second step is we integrate the result with respect to y. Then the integral is 0 to 3, 9.653 dy equal to 9.653y. Evaluate from 0 to 3. After completing both steps, we obtain a final value of approximately 28.9. The value represents the total volume under the surface. Okay, now let's see how GeoGebra helps us visualize this double integral. The first, we create the rectangular regions based on the given limits from x equal 0 to 4 and y equal 0 to 3. After that, we insert the function of f x, y equal to sin x plus 2, which appears as a three-dimensional surface. This is the picture. We can see this is the picture. The next, the surface is rectangular, and GeoGebra divides it into many small rings, representing the idea of Riemann sum. This is okay. Next, when GeoGebra adds all these small volumes together, it gives an approximation of the double integral. This is. Next, the result obtained is approximately 28.9, which is consistent with the manual calculating. This is the integral. The calculating is the same. So, this shows that GeoGebra helps us understand double integral both visually and mathematically. Next, the application of double integral. Double integrals are not only theoretical, but also useful in real-life application. They can be used to calculate the volume between two surfaces. If z equal to the function x, y and z equal to the function g x, y, then the volume between them is the double integral omega, the function x, y minus the function of g x, y dA. For example, in physics and in engineering. Next, the polar coordinate. For circular regions, polar coordinates are used x equal to r cos theta and y equal to r sin theta. The double integral omega, the function of f x, y dI equal to the double integral f, the function is r cos theta and r sin theta, r dr d theta. And the factor r appears due to change of coordinate. Okay, the last is the conclusion. At the beginning, we imagine how to measure water in a container that is not flat and not perfectly safe. Through double integral, we learned that complex surfaces can be measured by breaking them into small parts. With the left of GeoGebra, this concept becomes clear, not only through formula, but also through visualization. Hopefully, this presentation helps students see mathematics as useful and meaningful in real-life application. Okay, thank you for watching, and do not forget to like, share, and comment. If you have any question, feel free to contact me. See you next time. Thank you.